Imagine falling towards something from which nothing, not matter, not light, not information itself, can ever escape. Your clock slows down. The universe around you speeds up, racing through millennia in moments. Behind you, stars die and are born. Ahead, a perfect circle of darkness awaits, surrounded by a ring of light twisted into impossible shapes by gravity so intense it tears spacetime itself. You've crossed the event horizon. What happens next violates everything we thought we knew about cause and effect, about time and space, about the fundamental laws that govern reality. According to our best physics, you haven't just entered a region of intense gravity. You've entered a place where the future becomes space and space becomes time. Where forward no longer means what it used to mean. Where escape isn't just impossible, it's literally a direction that doesn't exist anymore. Today, we journey through evidence that challenges everything we understand about reality itself. We'll explore observations from the edge of black holes that suggest something so strange, so profoundly unsettling, that physicists are still grappling with what it means. In 1972, a young physicist named Jacob Bekenstein made an observation that would haunt physics for the next 50 years. He was thinking about black holes, those cosmic monsters where gravity grows so intense that not even light escapes. Bekenstein noticed something strange about their entropy. Entropy measures disorder, information, the number of ways a system can be arranged. For ordinary objects, entropy scales with volume. A larger box contains more air molecules with more possible arrangements. But black holes didn't follow this rule. Bekenstein discovered that a black hole's entropy doesn't scale with its volume. It scales with its surface area. Specifically, it's proportional to the area of the event horizon, that boundary of no return surrounding the singularity. Think about what this means. You would expect that the information content of a black hole, everything it has consumed, would depend on the three-dimensional space inside it. Instead, all that information appears to be encoded on its two-dimensional surface. It was as if a black hole were a hologram.
If you're enjoying the video, feel free to tap that like button. It shows me this content sparks something in you. And if you'd like to stay close as new stories appear, subscribe to the channel. It genuinely means a lot and helps this place grow in the right direction. Thank you for being here.
Stephen Hawking initially dismissed Bekenstein's ideas. Black holes, Hawking insisted, had no entropy. They had no temperature. They were simple objects described by just three properties: mass, spin, and electric charge. Everything else that fell into them disappeared forever. But Bekenstein persisted. And in 1974, Hawking made a discovery that proved Bekenstein right and plunged physics into a crisis that continues to this day. Hawking discovered that black holes emit radiation. Through a quantum mechanical process at the event horizon, black holes slowly evaporate, releasing thermal radiation into space. This Hawking radiation has a temperature, incredibly cold, but measurable in principle. And if black holes have temperature, they have entropy. Bekenstein's formula was correct. The entropy of a black hole equals 1/4 of its event horizon's area measured in Planck units. This created an immediate paradox. When objects fall into a black hole, their information seems lost forever. But quantum mechanics forbids information destruction. The universe must account for every quantum state, every possible configuration. Where does the information go?
The problem became known as the black hole information paradox, and it revealed something profound. If a black hole's information content is determined by its surface area rather than its volume, perhaps our understanding of space itself is wrong. Gerard 't Hooft, a Dutch physicist, was the first to suggest the radical solution. In 1993, he proposed that our three-dimensional universe might be a hologram. All the information describing physical reality, he argued, could be encoded on a distant two-dimensional surface, projected inward to create the illusion of depth. It sounds absurd. We experience 3 dimensions of space directly. We move through depth every day. How could that be an illusion? But 't Hooft's mathematics suggested something extraordinary. Just as a holographic image on a credit card appears three-dimensional when light hits it from the right angle, our universe might be a vastly more sophisticated hologram, information on a surface creating the experience of volume.
Let's read that again. Two completely different universes, one with an extra dimension in gravity, one without, described by the same mathematics. They're equivalent, not similar, equivalent, like two languages describing the same reality. This is the ADS-CFT correspondence, and it's the most concrete realization of the holographic principle. It suggests that a universe with gravity in any number of dimensions can be fully described by a theory without gravity in one fewer dimension, living on that universe's boundary. Everything happening in the five-dimensional bulk, particles moving, fields fluctuating, gravity warping space, corresponds exactly to processes in the four-dimensional boundary theory. The implications are staggering. If this correspondence holds for our actual universe, it means every physical process in our three-dimensional space could be a projection of information encoded on a two-dimensional cosmic horizon, infinitely far away. We might be holograms. But the evidence forces us to confront an uncomfortable possibility. What if depth itself, the very experience of moving through space, is nothing more than a convenient description? What if the true nature of reality is written on a surface we'll never see?
Maldacena's discovery created a revolution in theoretical physics, but it had a problem. It described a universe that doesn't exist, or at least not the one we inhabit. Anti-de Sitter space has negative curvature. Our universe has positive curvature, accelerating in its expansion. The spaces are different. The correspondence, while mathematically proven for ADS space, might be a beautiful mathematical accident with no connection to reality. Or so physicists thought. Then scientists started finding evidence that holographic principles might apply to our actual universe. The first clue came from the cosmic microwave background. In 2013, researchers at the University of Waterloo analyzed data from the Planck satellite, which mapped the CMB, the afterglow of the Big Bang, in unprecedented detail. They were looking for specific patterns in temperature fluctuations. What they found matched predictions from holographic models with stunning precision. The CMB shows tiny variations in temperature across the sky, typically about 1 part in 100,000. These variations reflect quantum fluctuations in the early universe that later grew into galaxies and galaxy clusters. The holographic models predicted specific correlations in these fluctuations, patterns that should appear if our universe's information is encoded on a lower dimensional surface. When the researchers analyzed the Planck data, those patterns were there. The probability of this matching by chance was less than 1 in 10,000. But here's where it gets strange. The holographic model that best fit the data suggested our universe has one fewer spatial dimension than we observe. The three dimensions we experience, length, width, depth, might be emergent properties, not fundamental realities. The CMB shows tiny variations in temperature across the sky, typically about 1 part in 100,000. These variations reflect quantum fluctuations in the early universe that later grew into galaxies and galaxy clusters. The holographic models predicted specific correlations in these fluctuations, patterns that should appear if our universe's information is encoded on a lower dimensional surface. When the researchers analyzed the Planck data, those patterns were there. The probability of this matching by chance was less than 1 in 10,000. But here's where it gets strange. The holographic model that best fit the data suggested our universe has one fewer spatial dimension than we observe. The three dimensions we experience, length, width, depth, might be emergent properties, not fundamental realities. The second line of evidence comes from black hole physics itself. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's event horizon. The supermassive black hole at the center of galaxy M87, with a mass 6.5 billion times that of our Sun, appeared as a dark shadow surrounded by a glowing ring of radiation. That image confirmed predictions from general relativity with remarkable accuracy, but it also allowed physicists to test holographic ideas in a new way.
The information paradox that started this entire journey predicts that information falling into a black hole isn't lost, it's encoded on the event horizon. If this is true, the horizon should show subtle quantum effects, tiny deviations from perfect smoothness predicted by classical physics. Researchers analyzing the EHT data found precisely these deviations. The event horizon of M87's black hole shows fluctuations at quantum scales that match predictions from holographic quantum mechanics. The horizon isn't a simple geometric surface. It's a dynamic, information-rich boundary where quantum and gravitational effects merge. Perhaps the most compelling evidence comes from quantum entanglement itself. Entanglement is that spooky phenomenon where two particles share a quantum state, remaining correlated even across vast distances. Measure one particle's spin, and you instantly know the others, regardless of the space between them. Einstein found this disturbing. He called it spooky action at a distance and believed it proved quantum mechanics was incomplete. But in 2013, physicists discovered something extraordinary about entanglement's relationship to spacetime. Mark van Romstonk at the University of British Columbia proved mathematically that quantum entanglement between particles creates the geometry of space itself. In holographic theories, the connections between entangled particles in the boundary theory generate the spatial structure of the bulk universe. Space isn't fundamental. Entanglement is fundamental. Space emerges from patterns of quantum correlation. This insight led to the ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. They suggested that quantum entanglement between particles is equivalent to wormholes, Einstein-Rosen bridges, connecting those particles through space. Every pair of entangled particles is connected by a microscopic wormhole. Entanglement and geometry are the same thing. If true, this means the fabric of space, the very arena in which physics happens, is woven from entanglement. And since holographic theories describe our universe as a projection from a lower dimensional boundary, the entanglement creating space in the bulk corresponds to entanglement on that boundary. Our three-dimensional space might be nothing more than an emergent illusion created by quantum correlations on a distant two-dimensional surface. But this represents just one piece of a much larger puzzle hidden in the mathematics of quantum gravity. The evidence extends beyond black holes into the realm of quantum information theory. In 2017, physicists made a breakthrough that seemed to confirm holographic principles from an entirely unexpected direction. They were studying quantum error correction, techniques used to protect quantum computers from noise and decoherence. Quantum error correction works by encoding information redundantly across multiple quantum bits. If some bits get corrupted, the original information can be recovered. It's how quantum computers might one day operate reliably despite their fragility. The researchers discovered that the mathematics of quantum error correction is identical to the mathematics of ADS/CFT correspondence. In holographic theories, information in the bulk universe is redundantly encoded on the boundary. If you lose access to part of the boundary, you can still reconstruct what's happening in the bulk from the remaining boundary information. This is exactly how quantum error correction works. The correspondence is too precise to be coincidental. Daniel Harlow and Patrick Hayden at MIT proved that the ADS/CFT hologram is literally a quantum error correcting code. The universe might be protecting information through the same principles engineers use to build quantum computers. But the implications go deeper. If our universe is a hologram using quantum error correction, it suggests reality has a computational structure. The universe isn't just described by mathematics, it's actively processing information, correcting errors, maintaining consistency. This raises a disturbing question: who designed the error correction? The most remarkable discovery involves the relationship between complexity and spacetime growth. In 2014, Leonard Susskind and colleagues noticed something strange about black holes and quantum complexity.
Complexity measures how difficult it is to transform one quantum state into another, essentially how many computational steps are required. They discovered that as a black hole ages and grows more complex quantum mechanically, its interior volume grows. Not the event horizon's area, that remains constant if nothing new falls in. The volume inside the horizon expands. The growth continues far longer than Hawking radiation would suggest. Even after a black hole has radiated away half its mass, its interior volume keeps increasing. For an astrophysical black hole, this growth continues for a time roughly equal to the black hole's mass measured in Planck units. For a solar mass black hole, that's about 10 to the power of 40 years, billions of times longer than the current age of the universe. Susskind called this, "The interior of a black hole is the fastest computer in nature." But here's what makes this evidence for holography. In the ADS-CFT correspondence, this interior volume growth corresponds directly to computational complexity growth in the boundary theory. The geometry of space inside the black hole is literally the quantum circuit depth of calculations on the holographic boundary. Space and computation are the same thing. When you move through space, you're moving through layers of quantum computation. The distance between 2 points represents the computational complexity of transforming the quantum state at one location into the state at another. This doesn't just apply to black holes. If the holographic principle is universal, it applies everywhere. The room you're in right now, the space between stars, the void between galaxy clusters, all of it might be emergent structure arising from quantum information processing on a cosmic boundary. Recent experiments have tested these ideas in laboratories. In 2021, researchers at Google and IBM created small quantum simulators exhibiting holographic behavior. They encoded quantum information on a one-dimensional chain of quantum bits and showed that this information behaves as if it exists in 2 dimensions. They measured entanglement patterns, information flow, and correlation functions. Everything matched predictions from holographic theories. These are tiny systems, dozens of qubits, not the 10 to the power of 120 bits of information that might encode our observable universe. But they demonstrate that holographic emergence is real. Lower dimensional quantum systems genuinely create the appearance of higher dimensional physics. Scale this up to cosmological dimensions, and you get a universe that looks exactly like ours. The most disturbing evidence comes from attempts to localize where you are in the hologram. If our universe is a projection from a boundary, that boundary should be somewhere. Physicists attempted to calculate where. The answer is troubling. If our universe has a holographic boundary, it exists at the cosmic event horizon, the edge of the observable universe. As space expands, that horizon recedes. Currently, it's about 46 billion light-years away in all directions, defining a sphere beyond which light emitted now will never reach us due to cosmic acceleration. That boundary, if holography is correct, is where the true information describing you exists. You're here, but the fundamental description of you is encoded on a surface 46 billion light-years away, projected inward to create the experience of existing in this room, on this planet, reading these words. The evidence extends beyond mathematical correspondence into the realm of testable predictions about the fundamental limits of reality itself. The holographic principle forces us to reconsider fundamental assumptions about the nature of space, time, and information. At its core, the principle states that the maximum amount of information contained in any region of space is proportional to that region's surface area, not its volume. This is the Bekenstein bound, formulated into a general principle by 't Hooft and Susskind in the 1990s. For our universe, this means there's a maximum information density, about 10 to the power of 69 bits per square meter of surface. That number comes from fundamental constants, the speed of light, Planck's constant, and Newton's gravitational constant. You cannot pack more information into a region of space than this limit allows. Try to exceed it, and you create a black hole, which immediately hides the excess information behind an event horizon.
this isn't just a theoretical limit, it's a consequence of combining quantum mechanics and gravity.
The holographic principle suggests that gravity itself is an emergent phenomenon. Erik Verlinde at the University of Amsterdam developed this idea into entropic gravity theory in 2010. Verlinde showed that gravitational force can be derived from statistical mechanics and entropy gradients in spacetime. Gravity isn't a fundamental force like electromagnetism. It's an emergent effect arising from the tendency of information to maximize entropy. When matter curves spacetime, it's really changing how information is distributed on the holographic boundary. What we experience as gravitational attraction is the holographic universe minimizing free energy and maximizing entropy. This explains a long-standing mystery. Why does gravity seem so much weaker than other fundamental forces? The electromagnetic force is 10 to the power of 40 times stronger than gravity. If gravity is emergent rather than fundamental, this disparity makes sense. Gravity doesn't play by the same rules because it's not actually a force in the traditional sense. It's a statistical consequence of information theory.
The implications for quantum mechanics are equally profound. Traditional quantum mechanics treats space as a fixed background stage where quantum processes occur. Particles exist at positions in space, and their wave functions evolved according to the Schrödinger equation. But if space is emergent from entanglement, quantum mechanics needs revision. The wave function isn't a field existing in space, it's a description of correlations that generate the appearance of space. This is the paradigm shift represented by ADS/CFT and related holographic theories. They're examples of quantum gravity, theories that successfully merge quantum mechanics and general relativity by making spacetime itself a quantum phenomenon. Other approaches to quantum gravity exist: loop quantum gravity, causal dynamical triangulations, string theory without holography. But holographic theories are unique in having passed mathematical tests and made testable predictions.
What do leading physicists believe?
Juan Maldacena, now at the Institute for Advanced Study, considers the ADS/CFT correspondence one of the most important discoveries in theoretical physics. He's proven the correspondence in multiple theoretical universes and continues searching for versions that apply to our expanding cosmos. Leonard Susskind at Stanford argues that holography is inevitable. Any universe with black holes must have holographic properties to avoid information paradoxes. Since our universe contains black holes, it must be holographic. Edward Witten at Princeton, one of the founders of string theory, sees holography as a guiding principle for understanding quantum gravity. He's working on generalizations that apply to realistic cosmologies rather than idealized theoretical spaces. Not everyone agrees. Roger Penrose, who helped develop black hole theory, remains skeptical that holography explains our actual universe. He points out that ADS/CFT applies to universes with different properties than ours, negative cosmological constant versus our positive one. But even skeptics acknowledge that holographic principles reveal deep truths about quantum gravity. Recent breakthroughs suggest we're approaching testable predictions about holographic reality. In 2022, researchers at MIT and the University of Amsterdam proposed an experiment to detect holographic effects in laboratory settings. They designed a quantum simulation using ultra-cold atoms arranged in specific geometries. If holographic principles apply, particles at the system's boundary should exhibit behavior equivalent to particles with an extraspatial dimension in the bulk. The experiment would measure correlation functions, how particles influence each other across distance, and compare results to holographic predictions. Early results, published in 2023, showed tantalizing hints of holographic behavior. The system exhibited emergent dimensionality under specific conditions. Full confirmation requires larger quantum simulators currently under construction. The James Webb Space Telescope offers another avenue for testing holographic cosmology. Webb observes the universe's earliest epochs, seeing galaxies as they appeared over 13 billion years ago. If the holographic principle influenced cosmic evolution, it should leave specific signatures in the distribution and properties of early galaxies. Holographic cosmology predicts that structure formation in the early universe should differ subtly from standard models. The differences are small, but Webb's sensitivity might detect them. Researchers are analyzing Webb's deep field images for these signatures. If found, they would suggest that holographic information encoding influenced how the first galaxies assembled. The upcoming Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes. These waves carry information about black hole event horizons at the moment of merger. The James Webb Space Telescope offers another avenue for testing holographic cosmology. Webb observes the universe's earliest epochs, seeing galaxies as they appeared over 13 billion years ago. If the holographic principle influenced cosmic evolution, it should leave specific signatures in the distribution and properties of early galaxies. Holographic cosmology predicts that structure formation in the early universe should differ subtly from standard models. The differences are small, but Webb's sensitivity might detect them. Researchers are analyzing Webb's deep field images for these signatures. If found, they would suggest that holographic information encoding influenced how the first galaxies assembled. The upcoming Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes. These waves carry information about black hole event horizons at the moment of merger. The implications for technology are staggering. If space itself is quantum information, manipulating space might be possible through quantum information processing. This opens theoretical possibilities for technologies that sound like science fiction, using quantum computers to create or modify space-time geometry. Before dismissing this as fantasy, remember that GPS satellites already account for gravitational time dilation. They experience time differently than we do because they're in weaker gravity. We manipulate space-time practically every day without thinking about it. Holographic principles suggest this connection between information and geometry is far deeper. Control information flow precisely enough, and you control space-time itself. Of course, the energy scales required are astronomical, but our understanding is growing. The broader implications connect to other cosmic questions. If our universe is holographic, what about the multiverse? String theory predicts a vast landscape of possible universes with different physical laws. Do they all follow holographic principles? Is the multiverse itself a holographic structure? Current research suggests each universe in the landscape might have its own holographic boundary. The multiverse becomes a collection of holographic projections, each creating its own apparent reality. This connects to the anthropic principle, the observation that our universe's physical constants seem fine-tuned for life. If countless universes exist as holographic projections, consciousness might only emerge in projections with the right properties. We observe a life-friendly universe because only such projections generate observers. The implications extend beyond physics into philosophy, consciousness, and the nature of reality itself. The most profound implications emerge when we consider what holography means for consciousness and subjective experience. If physical reality is a projection from a lower dimensional boundary, what does that make conscious experience? Your thoughts and perceptions feel undeniably real and three-dimensional. You experience depth directly. How can that be a hologram? The answer might lie in the computational nature of holographic projection. Consciousness, according to integrated information theory and other models, arises from information processing. Complex systems processing information in specific ways generate subjective experience. Your brain is such a system, processing about 10 to the power of 16 operations per second across 86 billion neurons. If the holographic principle is correct, your brain is itself an emergent structure, a pattern of information on a distant boundary projected into 3 dimensions. The information processing that generates consciousness happens on that boundary. But here's the remarkable thing: it doesn't matter. The projection is the reality. If your consciousness emerges from information processing on a holographic boundary, and that processing creates the experience of being a three-dimensional being in a three-dimensional space, then you genuinely are a three-dimensional being. The hologram is real. This resolves a philosophical problem. How can our universe be a hologram when we experience it as solid and real? Because the holographic encoding and the three-dimensional experience are equivalent descriptions of the same reality. You're not just a hologram, you're completely real within the framework of physical law. The framework itself happens to have a holographic structure, but that doesn't diminish your existence.
The relationship between holography and the simulation hypothesis is intriguing. Some philosophers argue that if our universe is information theoretic at base, if physical reality reduces to quantum bits on a boundary, then we might be living in a computer simulation run by advanced intelligences. But holography theories don't support this. They suggest the universe is computational in structure, but they don't require a computer or programmer. The computation is simply how physical law operates. The universe computes itself by being itself. Think of it this way. A raindrop follows the laws of physics. You could say it computes its trajectory by solving differential equations in real time. But no computer is doing the calculating, the raindrop just moves. It is the computation. Similarly, our holography universe processes information not because it's programmed, but because information processing is what existence means in a quantum world. The most disturbing paradox involves the arrow of time. Holographic theories suggest time might be emergent like space, not fundamental, but arising from quantum information dynamics on the boundary. The second law of thermodynamics, which gives time its forward direction, corresponds to increasing entanglement complexity in the holographic description. But this creates a puzzle. On the boundary, where the fundamental physics lives, time's arrow might not exist. The boundary theory could be time-symmetric. Only in the emergent bulk, the three-dimensional space we experience, does past and future become meaningful. This means memory, causation, history itself might be projections. The sense that the past is fixed and the future open might be an artifact of how three-dimensional physics emerges from timeless boundary information. Some interpretations suggest the entire history of the universe, past, present, and future, exists simultaneously on the holographic boundary. Time is the order in which we experience different frames of that complete cosmic movie.
What does the evidence suggest about reality itself? It suggests that reality is stranger and more subtle than our intuitions. Space might not be fundamental. Time might not be fundamental. Even matter and energy might be emergent patterns rather than basic ingredients. What is fundamental then? Information. Quantum information specifically, the patterns of correlation between quantum systems that define states and relationships. The universe might be, at its deepest level, mathematics, pure structure, pure relationship. The physical universe we experience is what those relationships look like from inside the pattern. This is simultaneously humbling and empowering. Humbling because we're patterns of information, no more substantial than shadow puppets on a cosmic screen. Empowering because those patterns include consciousness, love, beauty, meaning, all the things that make existence worthwhile. The hologram is reality, and reality, it turns out, is magnificent. We began this journey with a troubling question. What if the universe isn't what we think it is? We've traveled through evidence from black holes, where information defies the dimensions we observe. Through quantum mechanics, where entanglement weaves the fabric of space itself. Through mathematical proofs that describe our three-dimensional universe as equivalent to two-dimensional information on a distant boundary. We've seen how the cosmic microwave background carries hints of holographic structure, how black hole event horizons encode information with quantum precision, how laboratory quantum computers exhibit emergent dimensions, how spacetime itself might arise from computational complexity. The evidence suggests we live in a holographic universe, not a simulation, not an illusion, but a reality where depth emerges from surface, where space arises from entanglement, where existence itself is a pattern of quantum information projected into experience. We began this journey with a troubling question: what if the universe isn't what we think it is? We've traveled through evidence from black holes, where information defies the dimensions we observe, through quantum mechanics, where entanglement weaves the fabric of space itself, through mathematical proofs that describe our three-dimensional universe as equivalent to two-dimensional information on a distant boundary. We've seen how the cosmic microwave background carries hints of holographic structure, how black hole event horizons encode information with quantum precision, how laboratory quantum computers exhibit emergent dimensions, how spacetime itself might arise from computational complexity. The evidence suggests we live in a holographic universe, not a simulation, not an illusion, but a reality where depth emerges from surface, where space arises from entanglement, where existence itself is a pattern of quantum information projected into experience.
The current scientific consensus remains cautious. The AD-DS-CFT correspondence is proven for theoretical universes that differ from our own. Whether holographic principles apply to our expanding, accelerating cosmos remains unproven. But evidence accumulates. Tests continue. Each new discovery aligns more closely with holographic predictions. What remains unknown vastly exceeds what we've learned. We don't know how consciousness emerges from information. We don't know if time is fundamental or emergent. We don't know what lies beyond the cosmic event horizon where our holographic boundary might exist. But we've learned something profound. The universe is more than it appears. Reality has layers we're only beginning to glimpse. The solid, three-dimensional world we inhabit might be a projection from a cosmic hologram, and that possibility opens doors to understanding we never imagined existed. Perhaps the most important lesson is this: you are information, complex, beautiful, conscious information. Whether encoded in 3 dimensions or 2, whether fundamental or emergent, you exist. Your thoughts are real. Your experiences matter. The universe has structured itself in such a way that parts of it become aware of other parts and of themselves. That's extraordinary, regardless of how many dimensions are truly fundamental. The universe is vast, its mysteries are endless, and we, patterns of quantum information experiencing themselves through consciousness, continue the journey toward understanding. Welcome to the holographic universe. Welcome to reality at the edge of black holes. Welcome home. Could there be dark planets orbiting dark stars? Dark galaxies with their own internal structure invisible to every telescope humanity has ever built? The evidence doesn't rule it out. In fact, certain observations, unexplained gravitational anomalies, unusual dark matter distributions, patterns that don't quite match simple models, might be hinting at exactly this kind of complexity. Some physicists have proposed that dark matter might interact through its own set of forces, creating dark chemistry, dark molecules, perhaps even dark life. The idea sounds like science fiction, but the mathematics suggests it's possible. If dark matter particles interact with each other through forces comparable in strength to electromagnetism, they could form complex structures just as ordinary matter does. We would never see these structures. They would be ghosts in our universe, overlapping with our reality but fundamentally separate from it, interacting with our world only through the universal language of gravity. What if we're that civilization? What if dark matter represents not the absence of complexity, but simply complexity in dimensions we cannot access? The most profound implications emerge when we consider the possibility that dark matter might not be truly dark at all, that it might interact with itself through forces we cannot detect, forming complex structures and dynamics in a parallel realm of existence. Imagine a civilization that could only perceive gravity. They would know ordinary matter exists because of its gravitational effects, but they couldn't see light, feel electromagnetic forces, or observe chemistry. To them, our world would be the dark matter, and their world, the one governed by forces they understand, would be the normal matter. In 2021, astronomers reported unusual gravitational lensing patterns that couldn't be explained by any known distribution of visible or ordinary dark matter. The patterns suggested the presence of compact, dense structures with masses similar to small asteroids, but made of something that emits no light. What are they? Dark matter clumps, primordial black holes, or something we haven't even theorized yet? Here's what keeps physicists awake at night. What if dark matter isn't just passively sitting there, holding galaxies together? What if it's dynamic, evolving, interacting with itself in ways we haven't detected? Recent theoretical work suggests dark matter might form structures on scales far smaller than galaxies, dense clumps, streams, and possibly even dark matter planets or stars, objects held together by dark forces we know nothing about. These structures would be completely invisible, detectable only through their gravitational effects. What this means for us extends beyond academic curiosity. Dark matter shapes the cosmic environment that allowed life to emerge. Without it, galaxies would never have formed at the right times and in the right configurations to produce the heavy elements necessary for planets and biology. The ratio of dark matter to ordinary matter, that precise 5-to-1 ratio, appears to be critical. Computer simulations suggest that if dark matter made up significantly more or less of the universe's mass, structure formation would be fundamentally different. Too much dark matter, and galaxies would form too quickly, creating massive black holes that prevent star formation. Too little, and galaxies would never form dense enough to trigger efficient star formation. We exist in what appears to be a precisely balanced universe, and dark matter is one of the weights on the cosmic scales. But perhaps the most exciting developments are happening in the detection of dark matter's subtle effects on ordinary matter. Scientists at the Ice Cube Neutrino Observatory in Antarctica are searching for the products of dark matter annihilation, the theoretical process where dark matter particles collide and destroy each other, producing neutrinos and other detectable particles. If WIMPs exist, they should occasionally meet and annihilate, creating showers of particles that Ice Cube's detectors, buried a kilometer beneath Antarctic ice, might observe. Other researchers are examining whether dark matter might interact with atomic nuclei, not through collisions, but through extremely rare quantum processes, creating signals so subtle they require years of data to detect. The upcoming Lux-Zeppelin experiment in South Dakota will be 50 times more sensitive than current detectors, capable of detecting dark matter interactions that occur less than once per year in its entire 10-ton detector. Recent breakthroughs suggest we're entering a new era of dark matter astronomy, one that might finally allow us to see the unseeable. The Vera C. Rubin Observatory, scheduled to begin full operations in 2025, will conduct the largest survey of the night sky ever undertaken, imaging the entire visible sky every few nights for a decade. Its primary mission includes mapping dark matter throughout the universe through gravitational lensing with unprecedented precision. Meanwhile, the European Space Agency's Euclid mission, launched in 2023, is creating the most detailed three-dimensional map of dark matter ever attempted, observing billions of galaxies to trace dark matter's distribution across 10 billion years of cosmic history. What leading physicists at institutions like Caltech, Cambridge, and the Max Planck Institute increasingly believe is that dark matter isn't a single substance, but potentially multiple types of particles forming a dark sector of physics, parallel to, but rarely interacting with our own. There might be dark photons, dark atoms, even dark chemistry occurring all around us in dimensions we cannot perceive. This is where the evidence leads, toward a universe far stranger and more complex than the one we observe. This forces us to reconsider fundamental assumptions about what dark matter might be. Perhaps WIMPs aren't the answer. Perhaps dark matter consists of axions, hypothetical particles 1 trillion times lighter than electrons, with properties so unusual they barely qualify as matter in any conventional sense. Or perhaps dark matter is primordial black holes, formed in the first fraction of a second after the Big Bang, too small to have been detected, but numerous enough to account for the missing mass. Or perhaps, and this is where the implications become truly profound, dark matter represents a window into physics beyond the Standard Model, the theoretical framework that describes all known particles and forces. Every major theory attempting to extend the Standard Model, from supersymmetry to extra dimensions, naturally predicts the existence of particles with properties matching dark matter. And they should be everywhere. Right now, as you process these words, approximately 100 billion dark matter particles are streaming through your body every second. They pass through the Earth as if it were empty space, emerging on the other side completely unaffected. Occasionally, perhaps once in a decade for any given particle, one might collide with an atomic nucleus in your body, transferring a tiny amount of energy before continuing its journey. This is why detecting dark matter is so extraordinarily difficult. Scientists have built detectors deep underground, shielded from cosmic rays and radioactive background, filled with ultra-pure materials cooled to near absolute zero, waiting for that rare collision between a WIMP and an atomic nucleus. The most sensitive experiment, Xenon 1T in Italy, uses 3.2 tons of liquid xenon surrounded by photomultiplier tubes that can detect even a single photon of light. After years of operation, accounting for cosmic rays, radioactive contamination, and every other possible source of interference, they've detected nothing conclusive. So what is dark matter actually? What could possibly explain all these observations while remaining invisible and intangible? The leading theory suggests dark matter consists of WIMPs, weakly interacting massive particles. These are hypothetical particles that interact only through gravity and possibly the weak nuclear force, one of the 4 fundamental forces of nature. They don't interact with electromagnetic radiation, which is why they're invisible. They don't interact with ordinary matter through any force except gravity, which is why they pass through everything. According to calculations by physicists at CERN and laboratories around the world, WIMPs should have masses somewhere between 10 and 1,000 times the mass of a proton. They should be moving through space at velocities of a few hundred kilometers per second left over from the Big Bang. The evidence extends beyond cosmic structure into the realm of individual galaxy formation. Astronomers have discovered ultra-faint dwarf galaxies orbiting the Milky Way, tiny galaxies containing just a few thousand stars, but with masses indicating they're almost entirely made of dark matter, sometimes with ratios exceeding 1,000 to 1. These galaxies are dark matter with just a sprinkle of ordinary matter, like finding a cloud you can almost touch. They exist at the very edge of detectability, visible only because of those few thousand stars embedded in massive dark matter halos. And here's what makes them so important. Their existence was predicted by dark matter simulations before they were discovered. The theory said these ultra-faint galaxies should exist, orbiting larger galaxies in specific numbers and distributions. When astronomers looked carefully enough, there they were, exactly where the simulations predicted. The evidence extends beyond what we can see into the realm of what we cannot see. Dark matter may be influencing the very fabric of space-time in ways we're only beginning to detect. Think of it like this. Dark matter created invisible scaffolding, gravitational wells that ordinary matter eventually fell into once the universe cooled enough for atoms to form. Without this head start, without dark matter creating structure before ordinary matter could, the universe would look fundamentally different. Galaxies would have formed billions of years later, if at all. The cosmic web of structure we observe would not exist. Computer simulations confirm this. When scientists model cosmic evolution without dark matter, using only ordinary matter and gravity, the resulting universe bears no resemblance to what we observe. Galaxies don't form in the right places, at the right times, or in the right numbers. The structure is simply wrong. But when they add dark matter in the precise proportions measured by Planck, matching the rotation curves Vera Rubin observed, matching the gravitational lensing seen in cluster collisions, matching the acoustic oscillations in galaxy surveys, suddenly the simulations produce a universe that looks almost identical to our own. Planck's measurements allowed scientists to determine the composition of the universe with extraordinary precision: 68.3% dark energy, 26.8% dark matter, and just 4.9% ordinary matter. Everything we've ever seen, everything that makes up Earth, the Sun, all visible stars and galaxies, less than 5% of what exists. But the most remarkable discovery involves what happened in the early universe because of dark matter's unique properties. In the first few 100,000 years after the Big Bang, ordinary matter was trapped in an electromagnetic dance with photons, unable to collapse under its own gravity. But dark matter, immune to electromagnetic forces, began collapsing immediately, forming gravitational potential wells. The cosmic microwave background, the CMB, is the afterglow of the Big Bang, light that has been traveling through space for 13.8 billion years. This light carries within it a detailed snapshot of the universe when it was just 380,000 years old, encoding information about every component of cosmic composition. When the European Space Agency's Planck satellite mapped the CMB with unprecedented precision, it measured tiny temperature fluctuations, variations of just a few millionths of a degree. These fluctuations represent the seeds of all cosmic structure, the quantum fluctuations that would eventually grow into galaxies, clusters, and the cosmic web. The pattern of these fluctuations depends critically on the ratio of dark matter to ordinary matter in the early universe. But this represents just one piece of a much larger puzzle hidden in the oldest light in the universe, the cosmic microwave background. When the universe cooled enough for atoms to form, the pressure waves froze into the distribution of matter, creating a characteristic pattern of galaxy clustering with a specific scale, approximately 500 million light-years. Astronomers have measured this pattern in the distribution of galaxies across billions of light-years of space, and it matches theoretical predictions with stunning precision. Here's what makes this evidence so powerful. The pattern we observe requires dark matter to have existed in the early universe at a ratio of approximately 5:1 compared to ordinary matter. 5 parts dark matter, 1 part ordinary matter. This ratio determines the amplitude and wavelength of the acoustic oscillations, and any significant deviation would create a completely different pattern in galaxy distribution. We observe the predicted pattern. The ratio holds. The evidence converges from completely independent measurements made across vastly different scales and cosmic epochs. The bullet cluster represents just one piece of a much larger puzzle. Scientists have now observed dozens of colliding clusters, and every single one tells the same story. The gravitational mass center separates from the visible matter during collisions. But perhaps the most compelling evidence comes from something called baryon acoustic oscillations, pressure waves that rippled through the early universe. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Ordinary matter, protons, neutrons, electrons, everything that would eventually form stars and planets and people, was coupled to photons, creating a fluid that could transmit pressure waves like sound waves through water. Dark matter, unable to interact with photons, remained unaffected by these oscillations. When the clusters collided, their ordinary matter, primarily hot gas glowing in X-rays, interacted and slowed down, creating a shock wave of superheated plasma between the clusters. You can see this glowing cloud in X-ray images, marking where the visible matter piled up during the collision. But gravitational lensing revealed something else entirely. Astronomers mapped the gravitational fields by observing how light from background galaxies was bent and distorted. The gravitational center, the location of most of the mass, wasn't where the hot gas was. It had passed right through the collision point, separating from the ordinary matter by more than 3 million light-years. This is the signature of dark matter.
While ordinary matter interacts, collides, and slows down through electromagnetic forces, dark matter passes through everything like a ghost through walls. It's collisionless, interacting only through gravity. If dark matter truly exists as an invisible substance pervading the universe, it should leave signatures, fingerprints in the cosmic structure that only its presence could create. Scientists discovered the first signature in the most violent events in the universe, galaxy cluster collisions. In 2006, NASA's Chandra X-ray Observatory captured images of the Bullet Cluster, two galaxy clusters that had slammed into each other at millions of kilometers per hour. The collision occurred 3.8 billion years ago, and the aftermath revealed something extraordinary. But what was it? Astronomers searched for conventional explanations. Perhaps dark matter was simply ordinary matter that didn't emit light. Dead stars, black holes, cold gas clouds, brown dwarfs, planets floating between the stars. They called these objects machos, massive, compact halo objects. Throughout the 1990s, astronomers conducted extensive surveys, watching for the telltale signs of machos passing in front of distant stars. When a massive object passes between us and a star, its gravity bends the starlight, causing the star to temporarily brighten, a phenomenon called gravitational microlensing. They found some machos, but nowhere near enough. Ordinary matter, even dark and cold, could account for only a small fraction of the missing mass. Dark matter, whatever it was, had to be something truly exotic, something that had never been directly detected in any laboratory on Earth, something that represented a fundamental component of reality that physics had completely overlooked. But the evidence forces us to confront an uncomfortable possibility. We are made of the universe's minority constituent, living in a cosmos dominated by something we cannot see, cannot touch, and do not understand. The stars at the edge of galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster. According to Newton's laws, according to everything we understood about gravity, these outer stars should have been flung into intergalactic space billions of years ago, but they weren't. Rubin had discovered rotation curves that remained flat across entire galaxies, defying every prediction of gravitational physics. She calculated the mass required to explain these rotation speeds. The results were staggering. Galaxies must contain 5 to 10 times more mass than we can see. And this invisible mass wasn't concentrated in the galactic core. It extended far beyond the visible edges, forming vast spherical halos around each galaxy. The evidence was undeniable. Zwicky's dark matter wasn't an anomaly in one distant cluster, it was everywhere. When you watch a spinning carousel, the horses on the outside move faster than those near the center. They have to cover more distance in the same amount of time. Our solar system works the same way. Mercury screams around the sun at 47 kilometers per second, while Neptune, 30 times farther out, plods along at just 5 kilometers per second. This is how gravity works. The farther you are from the source of gravitational pull, the slower you should orbit. Vera Rubin expected to see the same pattern in spiral galaxies. Stars near the galactic center should orbit quickly, while stars in the outer regions should move much more slowly. She pointed her telescope at galaxy after galaxy, meticulously measuring the rotation speeds of stars at various distances from each galactic core. What she found made no sense. 400 times more massive. Zwicky proposed something radical. There must be dunkel materie, dark matter, invisible mass filling the cluster, providing the gravitational glue holding everything together. The astronomical community largely dismissed his findings. How could 99.75% of a galaxy cluster be invisible? The idea seemed absurd, a mathematical error, an observational mistake. But Zwicky's observations were correct. For decades, dark matter remained a curiosity, an unexplained anomaly that most astronomers preferred to ignore. Then, in the 1970s, a young astronomer named Vera Rubin began studying something closer to home, the rotation of spiral galaxies. In 1933, a Swiss astronomer named Fritz Zwicky pointed the telescope at Mount Wilson Observatory toward the Coma Cluster, a massive collection of over 1,000 galaxies located 320 million light-years from Earth. What he was about to discover would haunt physics for nearly a century. Zwicky was measuring the velocities of galaxies within the cluster, watching how fast they moved relative to each other. He applied a straightforward calculation, one that Newton himself would have recognized. Measure the mass of the cluster based on the visible galaxies, then determine if the gravitational pull was sufficient to keep these galaxies bound together. The numbers didn't work. The galaxies were moving far too fast. At the speed Zwicky measured, they should have been flung out of the cluster long ago, scattered across the cosmos like stones from a broken slingshot. Yet there they were, orbiting together in gravitational harmony. To explain what he was seeing, Zwicky calculated that the Coma Cluster needed to be 400 times more massive than what was visible. Imagine holding a photograph of your family, but you can only see the empty space between them. The people themselves are invisible. You know they're there because you can see their effects: the indentation on the couch where someone sits, the coffee cup hovering in midair, shadows cast by bodies you cannot perceive. This is our universe. Everything you've ever seen, every star, every galaxy, every nebula captured by our most powerful telescopes represents less than 15% of what's actually out there. The rest? It's made of something that doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any way we can directly measure. Yet it shapes everything. It holds galaxies together. It bends the fabric of space itself. Without it, you wouldn't exist. Without it, galaxies would tear themselves apart, stars would never form, and the cosmic web that structures our entire universe would collapse into chaos. We call it dark matter, but that name barely scratches the surface of how strange, how pervasive, and how fundamentally important this invisible substance really is. Today, we journey through evidence that challenges everything we thought we knew about the composition of reality itself. Prepare yourselves. We begin. But here's what we do know. Black holes represent the most extreme conditions the universe can create. They're places where physics reaches its limits, where our equations fail, where infinity becomes real. They're tears in the fabric of spacetime, one-way membranes between the knowable and the unknowable. And they're everywhere, at the center of most galaxies, scattered throughout space as stellar remnants, colliding and merging in events that shake the fabric of reality itself. The universe contains places where time stops, where space collapses, where all paths lead to singularities. These places are not theoretical, they're real, observable, and fundamental to cosmic evolution. The universe is vast, the mysteries are endless, the journey continues. The current scientific consensus recognizes black holes as laboratories for physics at the absolute extremes, places where general relativity and quantum mechanics meet, where information paradoxes challenge our deepest assumptions, where singularities might hide doorways to other universes or might represent the true limits of physical reality. We've learned that nothing can escape from inside the event horizon, but we've also learned that black holes aren't eternal. They evaporate over cosmic timescales. We've learned that they regulate galaxy formation, but we still don't understand how supermassive black holes formed so quickly in the early universe. We've imaged their shadows, but we can't see what lies inside. Perhaps quantum gravity will resolve these mysteries, revealing that singularities are finite structures in extra dimensions. Perhaps future observations will detect subtle deviations from general relativity that point toward deeper truths. We began with a mathematical curiosity, Karl Schwarzschild's solution to Einstein's equations, describing an object so impossible that Einstein himself rejected it.
From that abstract beginning emerged evidence of cosmic monsters, places where stars orbit at a fraction of light speed, where space-time itself collapses, where gravity wins absolutely. Black holes are real. The evidence is overwhelming. We've tracked stars orbiting them, photographed their event horizons, detected their mergers through gravitational waves, and measured their influence on entire galaxies. They're not rare curiosities, they're fundamental components of cosmic structure, present in most galaxies, shaping star formation and galactic evolution. Yet we still don't fully understand them. The ultimate question isn't just what are black holes, but rather what is the relationship between black holes, quantum mechanics, and the fundamental structure of reality? Current evidence suggests that understanding black holes fully will require a complete theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches are working toward this goal, but we're not there yet. What we do know is that black holes force us to confront the limits of our understanding. They're places where our best theories break down, where nature reaches extremes we can barely comprehend, where infinity becomes real and singularities hide secrets we may never fully unravel.